Okay, so now there is something I also want you to know. That's good to know. It's called the second derivative test. So it is important to know the content. So because the first derivative test involves this, what is it? Drawing this sine table, and it is a little bit lengthy. But that is the best algorithm we have. It works all the time if the function is continuous. But there is another algorithm which is probably you need to know because they can design questions that you have to use it somehow. So it is better to know about the content. So let us read the content and see what happens. It is very simple. It tells you that you have a function f and let x naught be in the domain of f. And you know that the derivative at x naught is equal to 0, but the second derivative is negative. Okay? If that is the case, you can immediately draw the conclusion and say that, okay, f has a local maximum value at x naught. So the first derivative is 0, it means it's the critical point, but the second derivative calculated at x naught is negative. Negative means local max. Okay? Number 2, if the first derivative is 0, it means that I have a critical point, and then the second derivative is positive, then you can draw the conclusion that that point is a local minimum. The third part is important to realize because the first derivative is 0, but the second derivative this unfortunately also becomes 0. It is very important, do not draw any conclusion. Anything can happen. It could be a minimum, it could be a maximum, it could be also an inflection point. Yes, or a terrace point in this case. Okay? So let us try to understand that. As you see here, this is not as powerful as the previous one because it doesn't talk about any singular points. So if you have singular points and you want to see if it's a local max or local mean, the second derivative test is not useful at all. It is useful for critical points if you want to recognize the character of critical points, max mean. And still there is one warning there. If the second derivative also turns out to be 0, don't draw any conclusion. Because I have seen many students think that, okay, if the second derivative is also 0, that is definitely a terrace point. That is not the case. For example, this is the most famous one. So let me describe the content. I give you a function, and you know that the derivative of that function calculated at x naught is 0. It means x naught is a critical point. A critical point is a candidate for a local mean, a local max, or a terrace point. Okay? How can I recognize this? If you take the second derivative and the second derivative is positive, then together you say local mean. X naught is local. And if you have f prime of x naught 0, but f double prime of x naught negative, yes, you can draw the conclusion that x naught local max. But if this one is 0 and you calculate the second one, it also turns out to be 0, no conclusions. Yes? Can be made. Regarding the character of the point x naught. So let me just give you this example. For example, if I give you these three functions, f of x equals to, so let me write it x to power 4, and g of x, x minus x to power 4, and h of x, x to power 3. And x naught is 0. Okay? If I take x naught to be 0, do you agree that f prime of 0 is 0 here? Do you also agree that f double prime of 0 is 0? So both of them are 0. The same is true here. G prime of 0 is 0, because this minus sign doesn't change anything. G double prime of 0 is also 0. Here, h prime of 0 is still 0. H double prime of 0 is also 0. But if you draw the graph of this function, it is like x squared but a little bit steeper. So this point is minimum, even though I have these two conditions. If I draw the graph of that function, it will be the other way around. So it will be a maximum. If I draw the graph of this function, it will be the other way around, something like that. It's a terrace point. So be careful, everything is possible. If the second derivative on top of the first derivative to be 0 is also 0, no conclusion can be drawn. And this simple example shows that, so don't do that, okay? Okay, so let me solve one problem for you of this type. Example number 4. I want you to see sometimes it really saves you time. Save time for you. For example, example number 4 in the notes, the function f of x is given to be x to power 4. And then I have 4 over 3 x cubed. And then I have minus 4x squared. Okay? So usually this second derivative test is useful if you have only critical points. If you have singular points, this is not useful at all. So you have to use the first derivative test. So if I want to find the local extreme points for this function, let us see if I can use the content of the second derivative test. So I take the first derivative, and I see that the first derivative is 4x cubed minus 4x squared, and then minus 8x. And then you see that might be this second derivative test is suitable because I do not have any singular points. The derivative exists everywhere. Did I do something wrong or not? No. Okay, so the derivative exists everywhere, so there are no singular points. So might be that's a good idea to use. Is there something wrong? Is that okay?
Yeah.
Okay. So now I see that there are no singular points. So might be that is good if I jump to the second derivative test. Because if it works, it is a little bit simpler. Not always, by the way. If the function is complicated, calculating the second derivative might be even horrible. But this is very simple. So I first put the derivative equal to, so no...
4x squared should be positive, no?
What? Ah, this one is positive, yes. Singular, so. Yeah, say something, okay? No singular points. The derivative exists everywhere. Thank you for correcting. Yeah, that is correct. Yes, that's positive. Okay, so now I put it equal to 0. What happens? I factor 4x out, and then I will have x squared plus x minus 2 equals to 0. Yes? And then I have 3 points. This one is 0, and this one is 0. But this one is 0 using a factorization or PQ formula. One answer is 1, and one answer is minus 2. Yes, these are the numbers that I get by putting it equal to 0. All of them are critical points. The only stress that we should have is that if I calculate the second derivative and put one of them inside, it becomes 0. It means that then I have to do more or less everything. I have to go back to the first derivative because of that single point. Okay? But hopefully it will work this time. So now I want to use the second derivative test. I calculate the second derivative, which is also very simple in this case. 12x squared plus 8x minus 8. And now what I need to do is just plug in these numbers to see if they are positive or negative. So if I calculate f double prime of 0, f double prime of 0, this is 0, this is 0, I get minus 8. This is negative. According to the second derivative test, x equals to 0, local maximum. Local maximum. Okay, I calculate f double prime of the next number 1. I replace x with 1, so it becomes 12 positive. So this means that x equals to 1, local minimum. And then finally, if I am lucky for the next one, if f double prime of minus 2, I replace x with minus 2 here, so it is minus 16, minus 24, and this is 48. It's 24, yes? Am I right? If I put minus 2 here, it's minus 16.
Are the critical points right there?
What? Yes, I checked it. 0. If you put 0, it is 0. If I put 1 here, 1 plus 1 minus 2 is 0. That's correct. If I put minus 2 here, minus 2 minus 2 minus 4 plus 4 is 0. That's correct. Yes, if I put minus 2 now here, minus 16 minus 8 is minus 24, and this is 48. So it's 24, I think. Yes? So that's also positive. So this means that this test was very successful in this case, and it was faster, I think. So local. Yes? So if it works, it is faster. Yeah. But there is another theorem and there's another algorithm. Now this time we are interested in knowing the global maximum or the absolute maximum. Okay? So here, if I go to the board again, by the way, can a local minimum be higher than a local maximum? Yeah, it is possible. Yes, because for example, I can draw some picture like this. Yes, I can draw like this. I can go up and I can go down here. So this is a local minimum, this is a local maximum, but even the local minimum is higher. Okay? But sometimes when we want to maximize or minimize the function, even though local maximum and local minimum are also good to know, but most of the time we want to know the highest point and the lowest point. That is called the absolute maximum and the absolute minimum. Okay? And the next algorithm we want to talk about is that if I give you a function f and I give you a closed interval and I tell you that this function is continuous on this interval, some theorem, do you remember the theorem, guarantees that this function has a maximum and minimum on that. The min-max theorem. Okay, so it is guaranteed that this function has a maximum value, has a minimum value. The question is that how can I find them? So I want you to visualize it yourself. Can you look up at the algorithm yourself? So for example, if I have a continuous function on a closed interval, so let me take this a and b, let me draw solid lines because I want to include them. So if I start going from here and then I go up to here, so I don't know, for example, coming here. So what is the absolute maximum of this function? What is the highest point? So the highest point is here. What type of point is that? It's a local max. Okay? So the highest point can sometimes be on the local maximum. So local maximum is indeed a candidate for the highest point. And then let me draw it like this. So for example, like this. If I draw it like this, this is a singular point, but it might be also the case that I have the highest point at the singular point. So usually I need to investigate the local maximum points which are inside, but these are not the only candidates. What is the next candidate? For example, I can draw this picture like this. I can come here and then I can go higher.
The edge point.
The edge points. So this means that if your goal is to find the absolute maximum and absolute minimum of a continuous function on a closed interval, where do you look for? You look for internal singular points, critical points, but you should also consider the edge points. Okay? But how can I find the maximum and minimum? For all those points, you calculate the value of the function at those points and compare the numbers. The biggest one is the maximum, the lowest one is the minimum. Is that idea clear? So if I give you a continuous function on a closed interval, you more or less do the same thing as before. You consider the edge points, you consider the critical points, you consider the singular points, but then you have a bunch of them now. You put all of them into your function and get numbers at the end, and then compare the numbers. Among the list, you will have the highest value, that's your absolute maximum, and in that list, the lowest value is the absolute minimum. Is that clear? Okay. So if you don't mind, let me also solve one example of this type. Example number 5, I will concentrate on number 2. Okay? Example 5, question number 2, so that is the question. F of x is given to you, and I hope that you are not confused. I don't see it. What is this one? It's 3x to power?
2/3.
2/3. So 3x to power 2/3 minus 2x. And then you see that this function and an interval is given to you. And they want you to determine the maximum and minimum of each function. Or sometimes they emphasize, find the absolute maximum and absolute minimum of this function on that interval. First of all, you see that the indication that you have to use this algorithm is that an interval is given to you. So you want to find the maximum and minimum of that. Okay, is this possible? Do you think it is possible to use this algorithm for that? Yes, because the interval is closed. And is the function continuous on there? There, yes. Because this is the third root of x squared, so I don't have any problems. That function is continuous everywhere. So this means that I will follow this rule, these rules that I have written in this remark. But you already know that, so that's why I want you to understand, because memorizing all these algorithms is not easy. So you take the derivative. You don't need to find the domain here, because even if the domain is somewhere else, you are supposed to work only on this interval. So f prime of x is what? 2/3 goes down, so it becomes 2 to the power of minus a third, and then it's minus 2. And I would prefer to simplify it a little bit, so I factor a 2 out, and I would write it as 1 over the third root of x minus 1. No, because here I don't need to know the sign, so I can keep it like this. Or if it doesn't matter, I go one step forward. Well, this is your derivative. Okay, so what should I do first? I need to find critical points. So it means that I put the derivative equal to 0. So this means that 1 minus the third root of x should be 0, which is the numerator. And then what happens? X becomes 1. But here you shouldn't compare it with the domain, because we don't care about the domain, we care about the interval. Is that acceptable? Yes, it is within. So I will accept it. Unfortunately, it's also the endpoint. It doesn't matter. So, and then this is the only critical point. And then singular points. So is there any singular point for this? F prime of x does not exist.
At 0.
This means that the denominator this time should be equal to 0. So this means that x equals to 0. Is it acceptable for our case? Yes, because it belongs to. So if you don't mind, let me emphasize it here. This means belongs to. This also belongs to. Otherwise, you just throw it out. You don't need it, even though that is point you calculated, but you throw it out. Okay, and so it means that I got 2 points, but I also have 2 endpoints, -1 and 1. But coincidentally, one of them is the endpoint as well. So I have to calculate f of 3 numbers, f of -1, f of 1, and f of 0. So let us do that. Okay, so I calculate f of -1. I put -1 in my original function. What is the answer? So this becomes 1, 3 plus 2, 5. And I calculate f of 0, which is simple 0. And I calculate f of the other one, which coincidentally is both a critical point from a function and that one. Of course, in principle, this is not a critical point because it's an endpoint here, but it doesn't matter. So f of a 1 is what? I replace x with 1, it becomes 1. And in this list, the highest value is the maximum of my function, and that is the absolute maximum. It is really the highest point, and the lowest value is the minimum. So if I ask you what is the maximum value, when I say the maximum, I mean the maximum value, which is 5, and the minimum is 0. Yes? Is that clear? Okay, so this is also good if you want to do some optimization problems, yes? And you are familiar with the optimization problems. For example, optimization means maximizing or minimizing depending on what you are doing, yes? If you are a businessman, of course, you want to maximize your profit. That's optimization. And in the same time, you want to lower your loss, yes? So that's also an optimization, yes? So optimization depends, you want to do it in the best way you can with the sources that you have. Yes, available to you. Okay, so let us solve 1 or 2 problems of this type. So let me start with an example because you more or less know what to do. I want to describe the points. So example number 6. The question is that. So let me show you. Yeah, please also work on these exam problems before having the seminars. So let us concentrate on this very simple one. Example number 6. Among all pairs of non-negative numbers that add up to 5, find the pair that gives the largest value for the product of the square of the first number and the cube of the second one. Yes? That's the question we want to solve. So among all pairs of non-negative numbers that the sum is 5, we want to find the maximum of this quantity. The first one squared multiplied by the second one cubed. We want to see what the maximum is. So how do you solve the problem? So here, x and y, I will take them those numbers. According to the problem, we have some conditions on them. It is mentioned that they are non-negative. So let us write them in front of our eyes. So let me see if I'm recording it or not. Yes. So x and y is greater than or equal to 0. And we know something more about x and y. We know that they add up to 5. So let me write. This is the first sentence of the problem written in mathematical form. And then in optimization problems, you either want to maximize or minimize a quantity. That quantity, let me call it the target function. Okay, so let me show it with t. It doesn't matter, by the way, these things. So let me show t. T is my target function. According to the problem, what is your target function here? It is the product of the square of the first number by the cube of the second number. Here it doesn't matter which one you consider the first and which one you consider the second, so let us use alphabetic order. So the function that I want to maximize is this. Oh, sorry. X squared multiplied by, so I want to maximize t. Yes? So I call it my target function. In the next course, multivariable calculus, you will learn how to maximize the functions which depend on more than one variable with some constraints. So what you will learn in the future, you'll be able to solve this one. But even I know that, I will definitely not use that method because that would be a little bit tedious. This method that I'm going to describe is simple. So for this course, when you want to maximize a function, that function is not allowed to have more than one variable in it, because you have a learned differentiation of functions with more than one variable. But your target function clearly has two variables in it. So it is almost already guiding you to get rid of one of these variables in favor of the other. That's the first strategy you should have in mind. Okay? So what I will do, I will either get rid of x in favor of y, then I will have only y variable involved, or the other way around, I will have only x involved. That's up to you. And sometimes one of them algebraically is simpler than the other one. Is that clear? So for example, I don't know, if you don't mind, let me find y from here. Find x is better because I don't know, x, let me find x, it becomes 5 minus y. And then put it here. Then t becomes equal to, instead of x, I put 5 minus y squared, and then I have y cubed. But now I safely call it t of y, because that's only a function of y. So what type of function I'm facing? It's a continuous function. Do I have any closed interval in this problem? For example, I know that y cannot be negative according to the problem. So there is a limit from below, and that is 0. But do you think there is a limit also for y from above? Because if y is so big, if y is bigger than 5, then x turns to be negative, which is still not allowed. So it means there is a limitation for x. That's exactly what I want you to understand. So here y belongs to which interval? From 0 to 5. So if you now forget about everything you learned, what do you have? You want to maximize this, and you have a closed interval. So that is exactly that problem we solved. Okay, so that's this. The only difference is that there the function was given. Here you have to find your function and your interval yourself. And then when you have it, the problem reduces back to the same problem. So let us do that. What should I do? Because this function is differentiable everywhere, so there is no singularity here. So I need to take the derivative. I don't know which way you want to take the derivative. So that's why it's better to raise it to power 2 and simplify it. Otherwise, you have to use chain rule and the product rule. So if I raise it to power 2 25 times that, and 2 times the first one times the second one times that, and then this one to power 2 times that. Yes? So I am raising it to power 2 and multiplying it by y3. It doesn't matter. If you want, you can start differentiation here. But if you want to start differentiation here, you have to use the product rule. And this one is the chain rule. So you should be careful about not missing a minus sign. But let me double check my calculations. 25 times that correct. 2 times the first one times the second one.
That's correct.
That's correct, and that's what's correct. Yes? So now I take the derivative. The derivative is 75y squared minus 40y to the power of 3. And the next one is 5y to the power of 4. Can you confirm my calculation? Yes. And now I try to put it equal to 0 because I know there is no singular point. The derivative exists everywhere. So I am looking only for a critical point. So I have to put this derivative equal to 0. But between them I can factor a 5y squared. This one becomes y to the power of 2. This one becomes minus 8y. And this one becomes 15. Yes? And I put it equal to 0. This is also simple. You can do it in your head. Do the factorization instead of using PQ formula. So this is y minus 3 times y minus 5. Yes? So how many answers I will get? 3. 0, 3, and 5. Yes? So these are the critical points. And now you know what to do. I have to calculate t at 0. And by the way, these 2 points are also my endpoints. So t of 0, t of 5, and t of 3. So t of 0 simply is 0. T of 5 is again 0. But t of 3, I put it here, so it becomes 4 times, so it's 108. So I am looking for maximum. So what is the maximum of t? Is 108. Yes. And of course the minimum was clearly 0. Yes. Because x and y are non-negative. So it was very clear without even calculations that the minimum should be 0. Is that clear? So that's an optimization problem. But of course optimization problems could be extremely hard sometimes. Because you never know. For example, let me solve one more problem for you here. So which one we solve? Yeah, let us solve number 7. So find the height. So let me show you if you want. That's on the board, yes? So find the height h and radius r of a cylinder of largest volume that can be inscribed in a sphere of radius square root of 3. Okay, so we want to solve that. So it means that you have a sphere. This is your sphere. The radius of the sphere, if you don't mind, let me show it with capital R, square root of 3. But now I want to inscribe a cylinder inside that. So I want to inscribe a cylinder in this. For example, this is one of those. Yes. this, if I can do. This is one of those cylinders that I can inscribe in this sphere. By the way, how many cylinders I can inscribe there? Infinitely many. I can make it thinner and taller, but I can make it more flat and wider, yes? But among all these ones, I want to find the one with the largest volume. And then look at the question. They are not asking you about what is the largest volume. They are asking you find the dimensions of that cylinder which has the maximum volume. They can also ask, of course, what the maximum volume is, yes? So how should we solve this problem? Again, not to be confused, so it means that I am looking for R. R is the radius of my cylinder, and I want to find the height. This is the height, let me call this little h. And this is the center of my, so these points are important, because this is a little bit geometry. So I'm looking for these so that I want to make the volume of my cylinder the maximum possible. So the first thing is that, so you shouldn't get confused. You have to write your target function. What is the quantity you want to maximize in this problem? You want to optimize here is the volume. Volume, so you have to write a formula for the volume. Volume of the cylinder is what? Pi,
R squared.
this R squared, and then times h. Okay? Again, listen to what I told you before, okay? In this course, how many variables are? So this is your target function, you want to maximize this, but pi is a constant, but R and h are both variables here. Because you can make it narrow and taller, or you can make it flat and wider, so it means both R and h can, in principle, change. And in this course, this is not something allowed. I have to have only one variable involved. So this means that I have to get rid of one of them in favor of the other one. In this problem, it was given in the problem directly. In this case, and in harder problems, you have to be creative to find that relation yourself. So is there any way that I can find a relation between this little r and that h, and of course the information given in the problem? Yes?
If we go from the center to the very corner.
Very corner, very good. So if I go from here, for example, to here, this becomes exactly capital R, which is given, and then?
Yeah, and then that's half of, that's the radius.
That's the small r, and this one?
Is half of the height.
Is it half of the height? Exactly. And then I can write the Pythagoras theorem, and then I have my relation. Okay, so let us write that. So then I will write R squared is equal to h over 2 squared plus R squared. But this means that R squared here is what? Is 3. This becomes h squared over 4, and then plus R squared. Here you have your relation. That is what I told you before, okay? So here, in principle, it doesn't matter which one you eliminate in favor of the other one, but sometimes practically it is useful to do it one way, not the other way. So which one is suitable here? Do you think it is better to get rid of h and keep r, or get rid of r and keep h?
Get rid of R.
Get rid of r, yes? Because this r comes with the second power. If I want to get rid of h, I have to take a square root, and that makes the differentiation harder. Okay, so here, you have to also be a little bit flexible, and then of course think smart. Here I take r squared to be 3 minus h squared over 4. And then I put it back here, and then, so here, and then what happens, v becomes equal to pi, instead of r squared I will write this, and then multiply it by h. And then now safely I can call it as a function of h only, because it is h involved. And if you don't mind, let me multiply it, it would be easier, because product rule, I don't want to use it if I can skip it. This is my function. But you can also see, this is an optimization problem. In principle, you have to use that algorithm, because you want to find the absolute maximum. So do you have any interval here for me? So for example, h cannot be any number, yes? H from below belongs to 0. If it is just a disk, okay? If you don't like, you can take an open interval, but you have to take the limit then, okay? It's not that important here. But is there any upper limit for h? If I make it narrower and narrower and taller, then I will have a very narrow pipe, and in a degenerate case, what will happen? I will have just a line. So it means that what is the maximum?
2 root 3.
2 root 3. Yes. You can keep it open interval. Of course, I agree with you. These two cases are degenerate cylinders. But they are not imposing any problems because you know that in those cases you will get 0 as the volume, but you are not looking for the minimum, you are looking for the maximum. If you don't like it, you can open it up, but you have to take care of setting limit. Okay? Yes. And then everything is clear. So now you can completely forget about the problem and go back to your algorithm. You have a continuous function on a closed interval and your goal is to find the absolute maximum. So what should we do? There is no critical point, there is no singular point because this function is a polynomial function and it's differentiable everywhere. So I just take the derivative, it becomes 3 minus 3 over 4h squared. And then I put it equal to 0 and then I try to find h. So h becomes plus or minus 2. Yes, but of course in this limit h is only 2 and that is my point. So then I have 3 points, 2 endpoints and 1 critical point. I have to calculate v at 0 and v at 2 square root of 3, but you don't really need to calculate. Of course you can calculate, you can put these numbers back into the formula and in both cases you get 0. You already know that, you don't need to calculate. But then I have to calculate v of 2. So v of 2 is what? I put 2 in the function. So it is 1, 2, so if I put 2 here, 4, and then 2, 4, 4 pi. Yes, it is 4 pi. And then among these numbers, of course, 4 pi is my maximum. So the maximum volume is 4 pi volume units, whatever that volume is. But the problem is not asking you about the maximum volume. The problem was asking you about little r and little h. But that's very simple because this maximum is attained when I choose h to be 2. So the answer to the h part of the problem is h is 2. And if I want to find r, I put h back in here and I find r. Yes? I have to put it in my constraint. So instead of h, I put 2 here, r becomes the square root of 2. Yes, is that clear? Okay, so there are very good examples in the book. I think it's good to go through them yourself and try to solve them. Let us jump to the last part of this lecture today, and that is the notion of concavity. Any questions here? Yes, understandable? So, the optimization problems could be extremely hard because you need to know a lot of things. For example, you need to be good in geometry to be able to find this. Usually writing the target function is not hard, but finding the relation between different variables might be a little bit challenging. But by practice you will be better at it. And the last part of this lecture today is the notion of concavity and inflection points. I just want to go very quickly through it. So the definitions are written precisely in the notes, and of course I will update them. Sometimes I will update them. Whenever you want to study, please download the latest version from this. If you have saved it already in your computer, when you come to it and you want to study it, I really recommend you to find, because when I go home, I still think about how can I improve the notes. Okay, so about concavity, the idea is very clear. So first of all, in your book, you have only the word concave up or down, okay? In some books, they use concave and convex. For me, concave up, concave down is much easier for me to understand. So that is, I agree with the book in this way. So if you have a function of this, it's a sad face, this is concave down, and it's a happy face, it's concave up. So concave down, up. Okay, and that matters, for example. You know, for example, if I have 2 points of a function, on the graph of a function, and so how I want to get a feeling how they are connected, you can see that I can connect these, and I know the function is increasing, for example, between these two. I can draw it in that way, this is increasing. I can draw it in this way, that's also increasing, but everyone feels the difference between them. So what is the difference between them is just this concept. One of them is concave up, one of them is concave down. So it is important to be able to detect this behavior before seeing the graph. If you don't have access to the graph, but you want to understand by the rule of the function, how can I understand this behavior? Okay, so if I want to give you a feeling of that, so let us, for example, consider this one. Okay. So my intuitive definition, some other books use other definitions, which sometimes I find it easier. For example, if I give you a point on the graph and I ask you at this particular point, is this function concave up or concave down? This is not the way the book has defined it. The book has defined it on an interval. So for example, on this interval from here to here, the function is concave down. But you can also talk about the sign of the second derivative at this point. For example, if I give you this point and I ask you what is the first derivative at this point C, because then you can draw a tangent line and you see that the slope is positive, so you can say that the derivative of that function at C is positive. But I can also ask you the same question, what is your opinion about the second derivative at that point? Is it positive or negative? Okay. So then I will say that this one is negative. How should I understand that? This is the way we think. You draw the tangent line and ask yourself, in the neighborhood of that point, is it the case that the graph of the function is below the tangent line or above it? Yes? If it is below the tangent line in the neighborhood, close to that point, then you say that that point, the function is concave down at that point. And if it is the other way around, you say that the function is concave up at that point. This is not the definition used in the book. The book is talking about concavity on an interval. What they say that a function is called concave down on an interval if the second derivative is always negative there. Which is not a very intuitive definition why that second derivative being negative gives rise to this kind of behavior. Okay? But let us try to understand what the book definition is. So let us consider this is A, this is B. I want to somehow convince you that the second derivative at every point on this interval for this concave down function is negative. Can you see that why? Okay, so let me pick a random point x here and then pick up this point on the graph and draw the tangent line here. This has a slope. This slope, I call it k, but I will say that this is a slope which depends on x. Because if I start moving x, the tangent will change, so the slope will change. Is that right? Okay. Now, if I ask you, can you connect k of x to f of x itself? Yes, because you know that the first derivative of f at x is exactly k as x at x. Is that right? That's the meaning of the slope. So if this is the tangent line on this, at this point on this graph of the function f of x, I know that the derivative at x is equal to k of x. Yes? But now, intuitively, what type of function kx is on this interval from here to here? In other words, do you think that this function increases or decreases as I move x to the right? So let us say that x starts from here, the slope is this much, and I go to the right, and I increase x. By increasing x, what will happen? The slope will of course change. But do you see how it changes? So for example, if it is here, when I go higher and I go to the right, the slope increases or decreases. You see, I am here, then I go like this, decreases to 0, and if I continue, it is even decreases to negative values. So it means that if the function is concave down, what happens? From A to B, the k function is always decreasing. But we know that if a function is decreasing, it means its first derivative is negative. So hopefully I could convince you that k prime of x is negative on this interval from A to B. Do you agree with this sentence? So if I start from here and go to the right, the slope of the function for the concave down function always decreases. Is that clear or not? So this means that I can say that the first derivative of the slope is negative. Do you agree? But what is the first derivative of a slope? A slope itself is the first derivative of my function. So if I ask you what is k prime x is the second derivative of my function. So this becomes f double prime of x, which is negative. So that's the motivation behind the definition in the book. So this means that the second derivative is negative, means is an indication of concavity down. And if the other way around, if the second derivative is positive, it's an indication of concavity up. So that is what the definition in the book tells, but that's more or less the same. So for example, let me just ask you one more question. So if I draw a graph like this, if I ask you at this point, let me take it A. Can I say something about positiveness or negativeness of these two quantities? For this one, you consider this the tangent line, yes? So the slope is negative, yes? But what about f double prime of A?
Positive?
Yes, it is positive because in the vicinity of that point, the tangent line is, so the graph is above the tangent line, so it is concave up. So this is positive. Yes? When I go here, so when I go here, it would be this. So if I go here, if I draw this tangent line, the derivative is still negative. But what is f double prime of B? Negative as well. Yes? And then what happens exactly at this point? Yes, if you draw the tangent line there, the tangent line passes the function. So at some point on the left to this one, it is concave up, but immediately after that, it is concave down. If this happens, that point is called an inflection point. Okay? So that is an inflection point. Of course, you see that the terrace point is also an inflection point. Do you remember? I talked about terrace point, but that's also an inflection point. Because before that, the function is concave down, and after that, the function is concave up. But what is the main difference that we say terrace point sometimes? In your book, you don't have terrace points. But if I want to differentiate it, terrace point is an inflection point, and the tangent line is horizontal. But the inflection point, you don't have that obligation. One more thing that you need to know is that the tangent line should exist. Because, what about this one? What about this point? Do you think that that point is an inflection point? You feel it shouldn't, but I think it fits the definition because before this point, what is the function? The concave up, and immediately after the point, this is concave down. So it changed the concavity, but it is not considered an inflection point by definition because there is no tangent line there. Okay? So this, you shouldn't consider this an inflection point. But can you tell me what are the candidate points for the inflection point?
Second derivative is 0.
Second derivative is 0 is a good indication, but is it enough to only consider those cases?
Second derivative is undefined, maybe?
Yes, that is also another one. So if you want to find inflection point, what do you need to do? You need to calculate the second derivative and put it equal to 0, you get a bunch of candidates. And also the points that the second derivative does not exist. Okay? And then you get a bunch of candidates. And then you need to determine which one is the true inflection point. How do you do that? you need to have a table like this time, f double prime and f, and investigate the sign of f double prime if the sign is changing. Okay, because as usual there is no time, I put some very small examples there, you can do it yourself. But intuitively, can you draw a picture that you have an inflection point, but the second derivative does not exist there?
Cube root of x.
Yes. So yes, cubic root of x, this function. Instead of making it very particular, let me draw this function for you. And that's exactly your example. Okay? So this point, do you agree that this point is an inflection point by the definition? The tangent line exists, yes, and the inflection point, the concavity changes. This is up and then suddenly it becomes down. So by that definition, this should be an inflection point. But if I ask you what is the second derivative of this function at 0, what is the second derivative? Why it does not exist? Because you know the rule. If you don't know the rule, I just draw this graph for you. Why do you think that second derivative of 0 does not exist?
It has a division by 0. Somewhere.
No, the definition is it is defined. So f of 0 is defined.
But the derivative has a
The first derivative does not exist. Do you remember we had 3 types of points that the function is not differentiable? Vertical tangent lines, sharp points, and discontinuities. This is one of them. So if the first derivative does not exist, it is not possible for the second derivative to exist. Okay? So this is possible that if you are looking for inflection points, you have 2 types of candidates. The candidates that the second derivative is 0, and the candidates that the second derivative does not exist. But these are just candidates. You have to set up a table like this and understand if the second derivative is changing sign in passage of them. Those are, if the change of sign happens, those are the inflection points, not the other candidates that you got. So exactly similar for the timetable for the local extreme points, but this time for the second derivative. That's it. Understandable? Yeah, anyway, I couldn't follow. It would be better if I can give you one more example, but we don't have time for it. But if you have problems, please ask me or Glenn in your team. Okay? Any questions? Thank you very much.